So let's get started, right? So what I have just written down here is just in a nutshell, right, what we have been looking at, right? So we started off with this block diagram of the negative feedback closed loop control system, and essentially we discussed the big picture perspective, right? And the first block that we have started looking at was the system or the plant block. You know, like we figured out what class of systems that we are going to discuss as far as this particular course is concerned. Then what sort of mathematical equations would be used to essentially model those systems, right, or characterize those systems that happen to be linear ODEs with constant coefficients. So once we understood that concept, you know, like we used Laplace transform to essentially get the transfer function representation, right, of this particular class of systems, okay. And then we started looking at how we could use the Laplace transform to evaluate the system response, right. So we had two responses, you know, like we had done quite a few examples, right, and also both the mathematics behind it and also the physical explanation, right. So what is called as free response, you know, like which is due to the non-zero initial conditions, right, that come aboard. That part of the dynamic response is essentially the free response, right. So and the forced response is due to the inputs provided to the system, right. So that is the forced response, and both responses are equally important, right. So in practice, you know, like you can have non-zero initial conditions and an input, right, provided to the system. But please note that the moment we talk about transfer function representation and follow the process that we are using in this particular course, so we implicitly assume the initial conditions to be 0, okay. And how come that is acceptable? Because we, first of all, the first rationale is that like we want to look at what happens when we provide inputs to the system, you know, that is our primary motivation, okay. So how do specific inputs affect the output of the system, right? So that is our first motivation. So that's why we want to use the transfer function representation. And second, if it so turns out that, you know, like if we design stable systems, you know, like we would see that yes, there is going to be a component due to the non-zero initial conditions, but those will decay to 0, you know, as time progresses, you know, like so we'll revisit this part when we do a few examples, right. So let me repeat that statement once again. Suppose, you know, like you have a system's response to be comprising of the free response and the forced response, okay. Let me scroll up to see whether we have a corresponding example in this file. I don't think so, right. So let me pull up something else, right. So okay, so yeah, here it is, right. So for example, you know, in the very first page we have one, right. So if you look at the response due to the initial condition and the input, if you look at the first part, right. So since the denominator polynomial, right, has roots that are in the left of complex plane, if you take the partial fraction expansion of the first part, right. So what is it that we are going to get? We are anyway going to get, for any given values of y0 and y dot 0, we are going to get some terms which have e power minus 2t and e power minus 3t. Do you agree? Okay, the first part. Let's not worry about the forced response now, right? Just the first part alone, the free response. So what can you say about those terms as t tends to infinity? They will go to 0, right? So that, in a sense, you know, like yes, your short-term dynamic response is going to be affected by non-zero initial conditions. You know, all of us agree, right? But in the long term, as long as you essentially design stable systems, the response or the output or the contribution of non-zero initial conditions to the output function decays to 0 as time progresses. That is, it becomes very, very minimal. In the short term, it's going to be there. everyone agrees to that point, right? But in the long term, the output is going to be influenced by what is the input that we provide to the system. Okay, so that is why we are more interested in forced response in this particular course, and that also has to do with the notion of stability that we looked at, which was on bounded input, bounded output stability. Okay, so that was one more point, right? So and then we saw that when we consider the transfer function, we had poles and zeros, right? So poles were essentially linked to the stability of the system, right? So we want all the system poles to be in the left of complex plane for Bibot stability, right? That's something which we figure out. And if we had what are called simple poles or non-repeating poles on the imaginary axis, then for maybe one input or one class of inputs, depending on the location of that pole, the output was unbounded. For all other bounded inputs, the outputs were bounded, right? So that's something which we figure out. If you had even one pole in the right of plane, the output is unbounded for all possible bounded inputs. And if you have repeating poles on the imaginary axis, then the output is once again unbounded for any bounded input. Okay, that's also something which we figure out, right? So, so in a certain sense, people say that poles affect the nature of the system response. Okay, so essentially, whether the output becomes bounded or unbounded when you give a bounded input, right? Whether you have oscillatory response or let's say a smoothly monotonic response without oscillations and so on, right? See, for example, we looked at second order systems, right? I hope all of you had a chance to find the unit step response and unit impulse response as far as the remaining class of systems that I gave you yesterday, right? So if we looked at it, for an underdamped system, we are going to have an oscillatory response, right? Because why? We had complex conjugate poles. But for overdamped and critically damped systems, we had a real poles, right, on the negative real axis, right? So we see that, there are no oscillations, okay? So in a certain sense, poles essentially affect the nature, within quotes, right, of how the system responds to an input, okay? And zeros, as we have seen, they affect the dynamic response by influencing the residues that come about, right? What are residues? Residues are those coefficients which multiply the exponential terms, right? So zeros affect the magnitude of the residue and also the sign of the residue, right, as we have seen through some examples. So in a certain sense, they affect the shape of the dynamic response, okay? So in the sense that, they will affect the dominance of certain poles and which are near to them, okay? If you have a non-minimum phase poles, we know how the shape of the response is going to be, right? Non-minimum phase zero, sorry, right? So the output is going to go one way and then shift to the other way, right? So all those things are effects of zeros. And by and large, even if you look at the response of a higher order system, okay, in general, let's say, in general, if we have a higher order system, typically, let's say the planned transfer function, let's say, it's just some k times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn, okay? Then once again, if you calculate the unit step response, right, what you are going to get is essentially terms that involve the poles, right? So if the poles are non-repeating and are real, we are going to have exponential terms, right? If you have a quadratic term with complex conjugate poles, we are going to get a response which is very likely to be that of what we saw as an underdamped second order systems, right? So, and we can immediately observe that from the discussions that we had till now, that even for a higher order system, the poles located closer to the j omega axis, right, dominate the system response, right. That's why they are called as the dominant poles. You can have n poles in general, but the poles which are closest to the j omega axis dominate the system response. Okay, but of course that said, okay, but the presence of zeros would also affect this characteristic. Okay, so because if you have zeros close to these dominant poles, obviously the dominance is going to be reduced. Okay, as we go along, we will see, we look at more examples of such would influence the dominance. Let me put dominance within quotes. Okay, so that's what this is. Oops. Okay, so right. Okay, great. So that's an what to say, just a summary of what we have done, right. So starting from now on, right, what I am going to do is that, like, we are going to look at this controller block. Oops. Okay, so right, so essentially we look at the controller block, and today's class we'll start with the discussion of what choices are typically used. Okay, and then like we'll then put everything together and start designing. Okay, so that's what we are going to do, right. So let's look at the controller. Okay, so please note that the controller block is an entity. I am just only looking now at the controller, right. Till now we looked at the system block. So what did we look at till now? You know, like we looked at the system block, system or the plant, okay, to which we provide an input u of t and we get an output y of t, right. In the complex domain, once we take the Laplace transform, you know, like we had p of s to be the system transfer function, u of s and y of s are the Laplace of the input and the output respectively, right. So that's what we have looked at till now, right. So that block is done. So now we are going to look at the controller block. Okay, so if I want to draw a similar diagram for the controller, what is the input and output, input to the controller and output from the controller? If you look at the closed loop diagram, input to the controller is a error, right, which comes from the summing junction, right, and output from the controller is a control input, okay, u of t, correct. So if we go into the complex domain, what will happen is that, like, the controller transfer function, let's call it as C of s. So and then the Laplace of the error and the control input, and let's call them as E of s and U of s respectively. Okay, so C of s is the controller transfer function. Okay, so of course, you know, like in some references they would use for P of s, C of s, you know, like alternatives that are used, they would call this as G subscript P of s and G subscript C of s. Typically the character G is used for denoting transfer function, and they will put an what to say, subscript to tell us, you know, like whether they are talking about the plant transfer function or the controller transfer function. Both are what to say, equivalent notations. Okay, like I am just using P of s and C of s, right, so that it's just a matter of notation. No, you can use whatever symbol you want, but I am going to stick to capital P of s for the plant transfer function and C of s for the controller transfer function. Please remember that for us, G of s is C of s multiplied by P of s, right. We derived that closed loop controller transfer function previously, right. So that's what we have. Now the question is, you know, like of course, once we have this, please note immediately that U of s is going to be equal to C of s times E of s, right. So that's something which we can immediately figure out, right. Okay, so Now, what are the different choices of controller structures, like that are available to us? The simplest controller which is available is a binary controller, an on-off controller, like what people call as a bang controller, so okay. So see, for example, like many even like air conditioning systems, like you have this air conditioning system, what happens? Let's say, I keep the temperature at 25 degrees Celsius, and let's say the temperature increases 26 degrees Celsius, the compressor cuts in and it blows cold air. And let's say the temperature goes to 24 degrees Celsius, it cuts off, and then like it just blows, just the fan, it operates in the fan mode, right? So that's on-off control. So you just go in a range and you have only two actions. Either you switch it on or you switch it off. That's about it, right? So what is a control input structure that looks like? Like u of t is some u1. If let's say e of t is less than some e1, it's u of 2 otherwise. Okay, so just a generic structure, like so you can have multiple variants to this, you can give finer regions and so on, right? But in general, like let's say if the error is within a certain magnitude, you give one input. If it goes outside, you give another output. Okay, that's what this control structure would be like. Okay, so obviously, like it is not very effective in the sense that although it's very intuitive, like it may not be the best for the system, right, in many cases. So because it doesn't regulate continuously, right, so it just like cuts in whenever the error is beyond a magnitude and cuts off when it's lower than some threshold, right? So we are not going to consider such controllers in this particular course. Okay, we are going to look at other types of controllers. Okay, so but you should be aware of this. Okay, so this is what is called as an on-off control. Okay, but if you want to continuously regulate, say same air conditioner, what I do is that like I want to adjust the temperature, like in a more what to say, finer manner, right? So not just have the compressor blow cold air at one go and then cut off completely, right? Then what I can have is what is called as a proportional controller. Okay, so what is a proportional controller, which is also called as a P controller? This proportional term is abbreviated as P. Okay, so what this controller means is that, as the name indicates, the control input u of t is directly proportional to the error which is given. Okay, so the structure of the controller is that u of t is kp times e of t. Okay, so here like kp is what is called as a proportional gain. Okay, so in a generic sense I should say proportional controller parameter. Okay, but very commonly called as proportional gain. Okay, so obviously kp is a real number, right? It can take any value between minus infinity to plus infinity, at least from a mathematical perspective, right? So this immediately implies that if you take the Laplace transform, what happens to u of s? U of s becomes kp times e of s. This implies that the controller transfer function is going to be, what is going to be the controller transfer function in this particular case? It is just kp. Okay, so that's what we have as the structure of this controller. So this is the structure in the time domain, and this is the transfer function of the controller. Okay, so what are the advantages of this controller? The proportional controller is very simple in structure, right? So that is like you essentially get the error multiplied by a constant, and that's about it, right? So its structure is very simple, so implementation is going to be pretty straightforward, right? So it's not very complex at all, right? So that is a big advantage. And by and large, like this is the first controller we try out. Like when we want to design systems, like if you see that the plant transfer function is of a certain structure, proportional control will work out most of the times. Okay, we are going to learn what are those tricks that we need to look for, right? So what are those characteristics that we need to look for, okay, as we go along. But by and large, proportional controller is very effective, okay, very simple in structure also. But on the flip side, it so turns out that for certain classes of systems, a proportional controller alone would not be able to remove steady state errors. What do I mean by that? Suppose, once again, let me take temperature control of a room, right? Let's say I come and set my desired temperature as 25 degrees Celsius. Suppose if the room's model structure, okay, is of a certain type, we will look at what this type is, right, as we go along. It may so happen that I may never be able to reach 25 degrees Celsius, okay, I can maybe go to 24.5. but my temperature, or 25.5, okay, and my temperature will settle down there, okay. I can never go to my desired set point, okay. That means that my steady state error will not be 0 as time tends to infinity, okay. So in certain scenarios, it may not be able to remove the steady state errors, okay. But we will see what those scenarios are, okay, as we go along, okay. So to summarize whatever I just told, like the first point is that like it's very simple in structure, okay, but the con is, it may not, okay, leads to non-zero steady state tracking error. In certain class of systems. Okay, so that is a limitation or a con of this particular controller. Okay, that's proportional control. Okay.